Hi, good morning. This is Jagdish, Assistant Professor of EC Department, SNS College of Technology, Coimbatore. Today, in our video lecture series, we are going to discuss the material properties of wide bandgap semiconductors, which is coming under the Unit 1, that is WBG, that's wide bandgap devices and their application in the real world. Come, let's get into the topic. So, what is wide bandgap semiconductor? Means why it is so special? Why it has so popular means wide bandgap semiconductors permit devices to operate at much higher voltages, frequencies, and temperature than conventional semiconductor material like silicon and gallium arsenide. So, why we know band gap? Band gap is nothing but of the gap between the valence band to the conduction band. So, in the name itself, you can see wide band gap. That means wide band gap means the gap between valence band and the conduction band is very larger. So, it needs higher voltage. Or higher voltage, operating voltage, and frequency and temperature than the conventional semiconductor like silicon, germanium, and that and all we know that's a conventional semiconductors. So this is called a wide band gap semiconductors. Semiconductor. So why it is this wide band gap semiconductor is required means it has so many advantages. That is higher operating temperature, higher voltages, and higher switching speed. So higher switching speed means we know the semiconductor which is usually used for many applications, especially the switching. So switching is nothing but of changing the state between 0 and 1 and 1 to 0. So that switching speed will be very higher in the case of wide bandgap semiconductor. So these are all the advantages why we are going for the wide bandgap semiconductor. And here you can see the wide bandgap semiconductor, the popular wide bandgap semiconductors are silicon carbide and gallium nitride. So these are all the popular wide bandgap semiconductors which is used in the real world in many applications. The semiconductor materials, the the conventional semiconductor material like their property and the band gap is given over here. There is material germanium, silicon, and gallium arsenide. So the chemical symbol for germanium is Ge and silicon Si, gallium arsenide GaAs. Their band gap energy in the electron volt is 0.7 and 1.1 and 1.4 respectively. And the green shaded columns are indicated that is a wide band gap devices. That is a silicon carbide, zinc oxide, gallium nitride, diamond. So their chemical symbol source for silicon carbide, that is SiC, and zinc oxide ZNO, gallium nitride ZAN, and diamond C. So silicon carbide SiC, it has the electron volt of 3.3, and zinc oxide is ZNO, it has the electron volt of 3.4, and gallium nitride the electron volt of 3.4, and diamond C, it has the electron band gap of 5.5 electron volt. So these are all the corresponding electron volt and the chemical symbol for the various wide band gap semiconductors. And why wideband semiconductor devices? Why it is required? Because already we have a conventional semiconductors like silicon, germanium. Then why specifically this wideband gap semiconductors are needed means it has lower on resistance, faster switching speed that already discussed in the advantages. That has a faster switching speed and lower switching losses and higher operating temperatures, better thermal conductivity, smaller size, lower cost, high reliable and durable, high voltage blocking capability. So these are all the things why we are going for the wide band gap semiconductor devices. And the popular, most prevalent wide band gap technology in the use today is gallium nitrate and silicon carbide. So these are all the GaN and SiC are the two most prevalent wide band gap technology in use today. So compared to that, so that has a band gap of 1.12 electron volt. Gallium nitride and silicon carbide are compound semiconductors with band gaps that are around 3 times higher at 3.39 electron volt and 3.26 electron volt respectively. This means that both can support higher voltages and higher frequencies, though there are number of differences between two technology that impact how they work and where they are used. One difference between gallium nitride and silicon carbide is speed in terms of electron mobility, how quickly electrons can move through the semiconductor material. At 2000 centimeters square by Vs, gallium electron mobility is 30% faster than the silicon carbide, and electron mobility of 650 centimeters square by Vs. These differences play in the various applications. Based on the application, we can choose either gallium nitride and silicon carbide. And the higher electron mobility of gallium nitride, for example, makes it much more suitable for high performance, high frequency applications. This ensures very low capacitance, meaning it is easy to achieve higher frequency, which is why gallium nitride semiconductors are widely used in RF devices that switches in the gigahertz range. SiC, on the other hand, when with its higher thermal conductivity and lower frequency operation, is more suited for higher power applications, including the higher end voltages required in electron volt and data centers. Some solar power designs, rail tracks, wind turbines, grid distribution, and industrial medical imaging that do not always require high frequency switching but do need higher voltages operate to improve heat dissipation. The applications is given over here based on the electron volt and the application power. So the various applications is listed over here. That is low voltage DC to DC converter, PMC, PMIC, and point of load. And from that, various application is listed in this graphical representations. Thank you.